Hello, this is Miss Chisholm. I'm coming to you today to look at 3.4 in Calculus 1 in 1910. We're going to look at 3.4, the chain rule. So let me share my screen. Alright, so we're going to go over the notes for a little bit and then we'll look at some examples. 3.4 deals with the chain rule. So in this section, we'll be looking at finding the derivative of a composite function using the chain rule. So it's as if you've got an outer function and then a function within. Okay, that's what a composite function is. We will look at finding the derivative of a function using the general power rule. We'll simplify derivatives of a function using algebra. We'll find the derivative of a transcendental function using the chain rule. And we'll look at the derivative for the natural log function. And then also for exponential functions, look at derivatives of exponential functions that have bases other than just e. So one of the most powerful differentiation rules is the chain rule. So this is going to be our first look at it. This rule deals with composite functions and adds a surprising versatility to the rules that we have discussed previously. For example, let's compare the functions shown here below. So these functions on the left can be differentiated without the chain rule, and those functions on the right are best differentiated with the chain rule. So take a look here. You've got just a basic quadratic function here, a basic trig function, sin x, a basic linear function, and then a sum of two functions, a linear function plus a trig function, that we would just find the derivative of each individual term. Here, take a look at that first one. You've got the square root, the exterior function is a square root function, and then below it or underneath it is x squared plus 1, a quadratic function. Here, the second one, you've got sine, you got the sine function, but then you've got 6x inside of it or within it. This third one, you've got a polynomial on the exterior, you've got this exponent of 5 on the exterior, and then within, you've got a linear function, 3x plus 2. Here, you've got x, which is linear, plus the sum of tan x squared. So not only just tan, but now you've got an x squared function within the tan. So basically the chain rule states that if y changes dy, derivative of y with respect to du times as fast as u, and u changes du with respect to dx times as fast as x, then y changes the derivative of itself and the derivative of x, or u, with respect to x times as fast as x. And I know that's not as clear, but we're going to look at it with the actual function so that you'll see what I'm referring to when I say u, when I say du, which is the derivative of u, and with respect to x, and things like that. So here's the chain rule. Let's take a look. So let's suppose y is a function of u. Okay, so y is some function with some function u inside it. Okay, and it is differentiable. All right, it is differentiable with respect to u. And let's suppose u itself is a function with respect to x, and it is differentiable with respect to x. Then y can be written as a composite function, f of g of x, and therefore it is differentiable. It's a differentiable function of x. So in other words, the derivative of y with respect to x is equal to the derivative of y with respect to u, then times the derivative of u with respect to x. So it's as if you take the outer derivative here with respect to u, you take the outer derivative with respect to u, then you take the derivative of u, the inside function, with respect to x. Let's look at it like this. Derivative of the function with respect to x. And the function is composite, f of g of x. So f is the outer function and g is the function within x. So the first thing you would do is take the derivative with respect to, take the derivative of the outer function f, okay, keeping the inside the same, and then times the derivative of the inside. So you would take the derivative of the outer function, derivative of f, keeping the inside function the same, then multiplying that times the derivative of the inside function. Okay? Let me look at some examples. So when applying the chain rule, let that clear up some here. When applying the chain rule, it is helpful to think of the composite function f of g as having two parts, an inner part and an outer part. Okay, so that's what I was referring to on the previous page. So the outer function is f, and you can think of the inner function, well, the inner function is g, but you can call it u. You can call g of x, that inner function, you can call it g of x, or you can call it u. So when we think about the outer derivative, the derivative of y equals f of u, the derivative of the function y, which is f at u, or f of u, is the derivative of the outer function at the inner function u, in other words, with respect to u, times the derivative of the inner function. So it's the derivative of the outer function at u with respect to u, times the derivative of the inner function. Okay? So in order to apply the chain rule, you have to be able to view the function that you're given, the composite function. You have to be able to view it as two functions. You have to be able to see it as having an inner and an outer part. So what we can actually think of is, let's think about the decomposition or decomposing a composite function. In other words, breaking it apart or showing it as having two parts. So that's what we're going to look at here. So on this first few examples here, it says y equals, on part A, it says y equals 1 over x plus 1. Okay, and we're thinking about this as being a composite function. So think about it as if you've got a function within a function. So the first part, you've got a fraction. If you look at it, you've got 1 over this expression. But then notice the denominator is not necessarily simple itself, it's x plus 1. So what we could do is we could say, let the outer function f of x equal 1 over just x. And then where we had just x was replaced with x plus 1, because we can let g of x be the x plus 1. So if you were to think about these as composite functions, putting them together, you would get that function back. So let's take a look at that. Let's say y equals f at g of x. So where I have f, I would write f, 1 over x. But where I have the x, I would replace it with g of x, which means I would then have 1 over x plus 1, which checks back to that original function. So to decompose functions is to find the outer, or to find two functions of that one composite function, taking that one composite function and breaking it into two. And we're only doing this because we have to be able to recognize what the outer and inner function is in order to apply the chain rule. Let's look at part B. We've got y equals sine 2x. Now normally a trig function is just sine x, cosine x, tan x. It's not necessarily sine 2x or cosine 2x, okay? So what's happened here is instead of just having sine x, we have sine 2x, so we've got this 2x imposed within the function. So let's suppose we let f of x equal just the outer sine x, and then let's let where we had originally just x, let's let g of x be 2x. So you can check this. So to verify, which is what we did up here, we verified, put that. We can say y equals f at g of x. So we would take our outer function, sine, and where we have x, we would technically have g of x. that's where that becomes sine 2x. You're taking g of x and putting it into f of x wherever you see x. So we had sine x, we now have sine gx, and then we replace gx with this actual function. Okay? Let's look at these two, and then I think we'll be ready to actually look at the chain rule in just a minute. So here on part C, you've got the square root function, or square root on the exterior, and then you've got this polynomial, quadratic to be exact, underneath the radical. Okay? So let's suppose we let f of x equal the square root. So we gotta have the square root of x. We gotta have some function underneath the radical. So we're gonna have a simple function x. Now, that means where we had x originally, g of x was put in place of it. G of x is imposed within. So that means g of x is that expression, that whole expression underneath the radical. 3x squared minus x plus 1. And you can verify y equals f at g of x. So where you have f underneath the radical, you would replace that x with g of x, and then therefore g of x is actual function 3x squared minus x plus 1. Okay? Let's look at this one as well, one more. First thing I want you to understand is that tan squared x is the same thing as tan x squared. Okay? So it's not always clear when you see it written like this, but that just simply means you got a tan x squared. Okay, when we're dealing with trig functions, we can put the two within, written like that. But that means the same thing. Now, writing it like this, we're able to see that we've got a squared function in the exterior, and then we got tan x imposed within. So that means I can let f of x be my x squared function, and then g of x, therefore, is the inside function tan x. And I can always verify that. Y equals f at g of x. Then that would be where I take the f, I've got x squared, I would replace that with g of x squared. And I should have written that a little bit better. My apologies there. But that's g of x squared. Then g of x squared is tan x squared, which then can be written as just tan squared x. So just verifying. But the actual answer is you're decomposing, you're getting an exact function for f and an exact function for g. And here you're getting a function for f and a function for g, decomposing the composite function that you're getting, so that we can recognize the in and outer functions. Okay? So let's look at chain rule here. And then I think we need to mention the general power rule as well. Although we have talked about the power rule previously, you have a more general power rule that can be applied over pretty much any differentiable function as long as it has a power. Okay? So first, let's look at this chain rule problem here. It says use the chain rule to find the derivative of y with respect to x. Okay? So derivative of the function y with respect to x. We're finding dy over dx. This is another way to write derivative. So derivative can be y prime, or because it's a function of x, you can call it the derivative of y with respect to x. You might see either symbol, okay, when calling a function, or when calling or looking for a derivative of a function. Okay? So I'm looking for the derivative of y. So I'm going to write dy with respect to x. So let's take a look at what we have here. We've got an outer function, which is cubic. So I'm going to take the derivative for the outer part. I'm going to apply the power rule. I'm going to bring down the exponent, okay, and lower it by 1. then I need to take the derivative of the inside function as well. This is a chain rule. So yeah, you have other options as far as how you want you have to work this, but chain rule is the easier one. Could I expand this out and use the FOIL method, multiply it out twice, and then multiply it again a third time? Because that exponent means I have 3 of those. I absolutely could do that. But then after doing all that algebra, I would then still have to find the derivative of each term. So it's faster to actually apply the chain rule. So that's what I'm going to do. Okay? So I would take the outer derivative first, which means I bring down the exponent, keeping the inside the same, and lowering the exponent by 1. Okay? Then I would say times the derivative of the inside. The derivative of x squared is 2x, because I'm going to be bringing down the exponent and lowering it by 1. And then the derivative of a constant is just 0. So that would just drop off. So I would clean this up. So right now I have 3, and I've got x squared plus 1. There's the second power, and then I've got times 2x. So I would simplify that a bit more here. Bring the 2x up front with the 3, and that gives me 6x. And then I have x squared plus 1 all squared. Could I leave it like that? I see no reason why, unless they specifically say multiply or simplify all the way out or something to that effect. But that is the answer. But could I go further and simplify it? Sure. I could write x squared plus 1 2 times and then multiply those out, which I'll do. So if I do that, then I've got FOIL method, x times x, or x squared times x squared rather. That gives me x to the 4th. That would be first times first. My outer would be 1 times x squared. That would be a 1x squared. My inner would be 1 times x squared. So that would be also 1x squared. And then my last one on the last would be 1 times 1, which is just 1. So this is now 6x still on the outside, x to the 4th. 1x squared plus 1x squared is 2x squared. And then I got plus 1. And I could go ahead again, one more step, use distributive property, and multiply through 6x. So I end up with 6x to the 5th plus 12x to the 3rd plus 6x. Okay? Now let me explain something to you. When you're working these problems, no one technically is going to be none the wiser if you use the chain rule on that problem. So sometimes you have no choice, you have to use the chain rule, but sometimes you actually have options. So let me see if I can get some paper. I'm so sorry. Alright, so what I could have done, as opposed to using the chain rule, I actually could have simplified that early on at the beginning and then found the derivative using the power rule for each term. Now I would have had a little bit more algebra on the front end to do, because I would have had to have written x squared plus 1 3 times and say order. I would have had to have written this x squared plus 1 3 times and then multiply it out. Multiply it out twice and then multiply it a third time. So basically expanding it out completely, then taking the derivative of each individual term. So I could have done that. You can expand first and then apply power rule for derivatives to get the derivative. So we could have eliminated the need for the chain rule on this problem. Sometimes you have to use the chain rule though, but this problem you had options. Okay, so when I say expand it out, I mean multiplying it out, multiplying these two together maybe first, getting that, and then multiplying it by that third one again. Okay, expanding it out completely. All right, let's look at the general power rule. Here it says if the function y equals u of x raised to the nth power, or let me start over. The function y equals u of x raised to the nth power is one of the most common types of composite functions. It's actually kind of similar to the one we just looked at. The rule for differentiating such functions is called the general power rule, and it is a special case of the chain rule. We technically just applied it in a sense. So let's say we looked at it. The derivative, let's say you got this function y, you got this inner function u of x raised to some nth power. And let's suppose this inner function u is differentiable with respect to x. Okay? So what you would do is you would take the outer derivative, bringing down the n, bringing down the exponent, and reducing that exponent by 1, and then taking the derivative of the inside of u. Taking the derivative of the function inside, taking the derivative of u. So that's where you got times derivative of u with respect to x. So this is essentially what we just did, okay? We applied the chain rule, which is basically us applying the power rule for the outer function and then taking the derivative of the inside, okay? You could also think about it as being written, instead of using the du over dx, you can write it in terms of u prime. So derivative of the outer function, bringing down the n, lowering the exponent by 1, so that's where you see n minus 1, and then times the derivative of u itself. So that's where you see times u prime. Okay? Okay. So we'll look at maybe another problem here, and then we'll look at some homework problems. All right, so this problem is similar to the one that we just worked. You've got an outer exponent, a cube function, and then you've got a quadratic on the inside. So I'm going to take the derivative. I'm going to take the derivative of f of x and call it f prime of x. So I would bring down the exponent 3, keeping the inside the same. And I would lower that exponent by 1. So 3 minus 1 is 2. Then I would say times the derivative of what's inside. So what's inside has 2 terms, so I take the derivative of the first term, which is just 3, and I say minus the derivative of the second term. The second term has a coefficient of 2 already, so I'm going to bring down the exponent of 2. It's going to multiply to the 2 that's already there, and then I'm going to say lower the exponent by 1. So that becomes 4x. Okay? So what I'm going to do is I'm going to bring, let's see, I'm going to rewrite this a little bit. I may not simplify it all the way necessarily, but I can clean it up a little bit. One good thing is that the homework is not going to require you to simplify it all the way down to do all that algebra. It's not going to make you. But what I will do is try to at least bring it to where I don't have a factor here or a common multiple here, and then this binomial. I'll at least bring those together. So I'm going to write 3, and then 3 minus 4x, and then I'm going to write 3x minus 2x squared, and then I got that all squared there. So I'm going to distribute here. That gives me 9 minus 12x, and then I still have times 3x minus 2x squared, all squared. One last thing, if you wanted to, you could show this as that binomial, and then you got 2 of these, if you wanted to. But it's not necessary to go any further than that. That's the derivative. That's all it's asking for. Okay? I would probably just leave it like that. If I did anything else, the only thing I would do is, since these match, is multiply those out. Multiply these together using the FOIL method. But I would keep the 9 minus 12x, and I would multiply this out using the FOIL method. I would get this first times first would be 9x squared, The outer would be a minus 6x cubed. The inner would be a minus 6x cubed. And the last would be a plus 4x to the fourth. And then the two in the middle come together. So this would be 9 minus 12x times 9x squared minus 12x cubed plus 4x to the fourth. And I would definitely pause it over there. Honestly, I might as well just stop right here. Either one, it'll take it. Okay? All right, let's look at number 4, and then I'll look at some homework problems too. But these are pulled from homework, they're similar. Number 4, you've got g of x equals 2. This is a multiple of 2 here, a constant multiple. And then you got fourth root, that little 4 is the index, fourth root of 9 minus x squared. Okay, so the first thing we do is we write that root, that radical, as a rational exponent. So g of x equals 2, parentheses, 9 minus x squared raised to the 1/4 power. Remember, radicals can be written as rational exponents. Now we're ready to take the derivative. So now we're looking for g prime. So I keep that 2. I take the outer derivative. Okay, remember we take, because it's a power on the exterior, take the outer derivative. So we're going to bring that 1/4 down. Keeping the inside the same, we lower that exponent of 1/4 by 1. Then we say times the derivative of the inside. The derivative of a constant is just 0. The derivative of negative x squared becomes a minus 2x, negative 2x. Okay, and I use parentheses so that you don't think that's a minus. That's actually just showing that this term here is negative. That is the derivative of the inside. So it's the derivative of the exterior, or the outer function, times the derivative of the inside function. So this ends up being 2/4, which will reduce, times 9 minus x squared raised to the negative 3/4, so that's 1/4 minus 1, times negative 2x, okay? So I've got 1/4, right here, 2 over 4 is 1/4, and then I'm going to bring that negative 2x here, negative 2x, put x on it. And then I've got this. I'm going to write that as 1 over 9 minus x squared to the positive 3/4. Okay, and we have to write that exponent positively. So this simplifies right here. I'm sorry, that's not 1/4, that's 1/2. That's 2 over 4 is 1 over 2, okay? So what happens here is the 1/2 and that negative 2 cancel. You still have the negative x. I'm going to just put that on top there, where that 1 is. And then I've got over 9 minus x squared raised to the 3/4 power. And that's your derivative. No reason to go back to the radical. Just leave it as is. Okay? Alright, let's see what our homework looks like here. So the first few problems, I'm going to walk through some of these. The first few problems are asking you to complete the table. Basically, it wants you to decompose the function. So on number 1, you're given your composite function, f of g of x, and it is 3x minus 4 to the 8th power. So the first thing they want you to do right here, when you complete the table, you're going to look and see what did they give me. Well, they want you to find the outer function. Well, actually, the outer function is given. Okay, so we're writing y equals f at u, or f of u. In other words, we're replacing f and g of x. We're writing them in terms of u, y and u. So the outer function is that 8 there. If we call that inner function u, then that is u to the 8th power. So that's what you have right here. We're calling the inner function u. So you would have y equals u to the 8th power. And u is this inside function, 3x minus 4. So that goes right here. Okay? If you were to look at this part, they give you the outer function. Okay, so if you think about it, you've got y equals, your composite is y equals 5 over the square root of x squared plus 11. So you've got this x squared plus 11 imposed within this radical. So let's say we call the outer function 5 over square root of u. Okay? And that's what we have here, 5 over the square root of u. So u, therefore, would be that inner function underneath the radical, which is x squared plus 11. So you're looking at the functions, and you're basically trying to rewrite them. You're looking at the composite function, and you're trying to rewrite them as separate functions in terms of u, where u is g of x, which is a function of x. Again, here you've got an outer cube function, but you got ln of x within, and composed or decomposed or imposed, I should say, on the inside. So the outer function you can say is u to the third power, which is what they have here, and that means the u would be the ln of x, the inside function. Okay? So it's like you're kind of decomposing in a sense, or composing. You're giving a composite function, you're writing it in terms of u. Alright, let's take a look at a couple of derivatives here on this page. Again, I did some in the notes. They're very similar. These start out really similar. Look at number 4. You've got g of x equals 2, and then you've got parentheses 4 minus 9x to the fourth power. Uh-oh, it's clear now. So we're looking for g prime. Alright, well, let's say we write g prime of x then. The first thing we're going to take the outer function, take the derivative of the outside. In other words, we're going to bring down that 4. So you can use 4 minus 9x on the inside, keeping that the same. And you're lowering the exponent by 1. And eventually I'm going to get to where I just write 3. Okay, I won't necessarily write 4 minus 1, but right now I'm still showing all my steps. Then I say times the derivative of the inside. The derivative of the constant is just 0. The derivative of minus 9x or negative 9x is a negative 9. Okay, so this is 8. And then you've got 4 minus 9x to the third power times negative 9. Go ahead and multiply the 8 and the 9 together. And you've got a negative 72, 4 minus 9x to the third power. And notice that they left it. You do not have to expand that out. You do not have to FOIL and simplify that all the way out. Leave that answer as is. You find the derivative. Okay? Let's do it up here. Number 5 is similar to the one I did in the notes as well. You've got your outer function, your outer derivative that you're going to take. So let's say x prime of t. I'm going to bring down the exponent, keeping the inside the same. And you're going to lower that exponent by 1. Then you're going to say times the derivative of the inside. That would be times 3. So we took the outer derivative, we brought 2/3 down, and lowered the exponent, the 2/3 exponent by 1. Then we say times the derivative of the inside, which would be times 3. So 2/3, what I'm going to do is bring that 3 to the front, and then I've got 3t plus 1. 2/3 minus 1 would be a negative 1/3. Okay? The 3 on the bottom cancels with that 3. And then I'm going to write this with a positive exponent of 1 over 3t plus 1 raised to the 1/3. And so that is 2 over 3t plus 1 raised to the 1/3. Or you can actually write that as a radical. Sorry, I keep getting this. Or you can actually write that as a radical. 2 over cube root 3t plus 1. And then I actually didn't need the parentheses anymore, but anyway. Okay? The homework actually kept it with the radical, so you can as well save yourself some work. Okay? But those are equivalent, whether you keep it with a rational exponent or you rewrite it with a radical. Alright. That one's similar. You would first write y with a rational exponent, the exterior function. So you got 9x squared plus 5, and then that's raised to the 1/3 power. So you would take the outer derivative first, bring it down, keeping the inside the same, lowering that exponent by 1, and then saying times the derivative of the inside. Derivative of 9x squared is 18x. Derivative of 5 is just 0. Every time I use my pen, it gets a little big. Okay. So of course you would clean this up. So we got 1/3. This is 9x squared plus 5 raised to the negative 2/3. And then I've got times 18x. Alright. I have to make exponents positive, so that would definitely go to the bottom. And I'm going to bring the 18x over here with the 1/3 because I think that'll reduce. 3 goes into 18 6 times. So I'm going to write that together. And I'm going to write this part as 1/9x squared plus 5 raised to the positive 2/3 exponent. Okay? So all I have to do then is cancel out 3 into 18, which is 6. So on top of that, 6x, and on the bottom, 9x squared plus 5 raised to the 2/3 power. And I would leave it like that. There's no reason to break it down. Notice how here they went back to the radical, okay? And maybe they did that because it started out as a radical, but I have seen some problems where it starts out as a radical and they still left it as a rational. So either way, your answer will be accepted, okay? Whether you leave it as a rational exponent or you rewrite it with the radical, because that denominator is 3, indicating a cube root. So we got cube root, radical 3, and then the 9x squared plus 5 squared is underneath the radical. Okay? Let's see if there's anything else I wanted to show y'all before I close that video, the video for today. Let's see if there are other problems. Ooh, yeah. That one's ugly. So yeah, number 10, let me just kind of talk about it, even if I don't work it all the way. You would be applying the chain rule for the outer function, and then notice the inside function is a rational function, so then you would have to apply the quotient rule on the inside. Remember the quotient rule says bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So you would have to do all of that. Let me show you what I mean here. The first thing that they did is they actually made the exponent positive before they even moved with it. And I recommend that. If you've got a rational function and it's raised to a negative exponent, you can just flip it and raise that to a positive, change that exponent to a positive. That way you can work with positive exponents as opposed to negative. So then when you take the outer function, the outer derivative, you would bring down the 2, keeping the inside the same. And then you would say times the derivative of the inside. Well, the inside is a quotient, so you would have to apply the quotient rule. So you would say bottom times the derivative of the top minus the top times the derivative of the bottom. And that would be all over the bottom squared. And so from that point, it's literally algebra, cleaning this up, okay? Cleaning it up. So because you're multiplying, you basically are multiplying a fraction times a fraction. So you multiply across, top times top, bottom times bottom. So we still got this 2 here, okay? They cleaned all this up on the inside here and got this. And then they're saying this times that, because it's top times top. The bottom is a 3x squared minus 2 over here and a 3x squared minus 2 squared over here. So you got three of those. Notice that a exponent now is a 3. So you got 3x squared minus 2 cubed. Continuing to clean this up, you multiply or FOIL or multiply through here. Actually, you can pull out a common factor from these. And you can also pull the negative out. So that's what they did. They pulled the negative out front. Okay, and they pulled out a 2 from all of those terms. They had all these 3 terms have 2 in common. So that's where the 2 that pulled out of these comes up front and multiplies with that 2, and that's where we got 4. Okay, and that's all they did. They didn't clean it up any more than that. They kept the 2x plus 3, and then once they pulled out that negative 2 and it came up front, they were left with this. So this simplified to this, and you pulled out the negative 2, and then you kept the denominator the same. Okay, so it's a lot of algebra. Once you actually take the derivative, it's quite a bit of algebra cleaning it up. Let's see here. You got a few trig functions that you'll take the derivative of. Like, for example, I think these might be the easier ones, honestly, because even though it's a trig function, we know what the derivative of sine is, which is cosine, okay? So we're looking for the derivative of y, which is 2 sine of 2 pi x. So this 2 is just a constant multiple, so you're going to keep that. But the derivative, the outer derivative, which is the sine, the outer derivative, the derivative of sine is cosine, and you keep the 2 pi x the same. Then you say times the derivative of the inside. The derivative of 2 pi x is just 2 pi. Why? Because pi is just a constant, just like 2 is. Think about it. The derivative of 2x would just be 2, so therefore the derivative of 2 pi x would just be 2 pi, because pi is just a constant. It's just 3.14. Okay, it's just symbolic. So then cleaning this up a bit, 2 and 2 come together to give us the 4. Put the pi up front as well, and then you got cosine 2 pi x. And that's your answer. Okay? Similar here. You would take the derivative, the outer derivative, which is the tan. The 9 is a constant multiple. So the derivative of g prime, you would keep the 9. The derivative of tan is secant squared, keeping the inside the same. And then taking the derivative of the inside, derivative of 8x is just 8. So you get 72 secant squared 8x. And they wrote it as secant 8x, and they put the 2 on the outside. Those are equivalent. Those are equivalent. They mean the same thing. Okay? Alright. I think that's pretty much what I wanted to go over. Let me make sure there's not another rule we need to talk about, because it might be. Here, we kind of just applied it, but when you're dealing with the chain rule over trig functions, over transcendental functions, trig functions, transcendental functions, same thing. They're functions that have movement, transcendental. You would take the outer derivative and then the derivative of the inside, which is just whatever the derivative of u is. So the outer derivative of sine is cosine, keeping the u the same, and then times the derivative of u itself. Okay, which is what we kind of just did. Then you've got the derivative of the natural log. Okay, the derivative of ln of x is 1 over x. If you have a function within ln, such as u, you would take the outer derivative. The derivative of ln of u would be 1 over u, and then you would say times the derivative of u itself with respect to the x. Okay? Let me give you an example of that with this one here. So the derivative of ln of 2x would be 1 over 2x, and then we would have to say times the derivative of the 2x, which would be times 2. And that would end up being 2 over 2x, which is still just 1 over x. So it ends up simplifying really nicely. Okay? Let me see. Is there anything else? Oh, yes. Sometimes you may have exponential functions that have bases other than e. So we need to think about that as well. There is a derivative for an exponential function with the base a. Okay, so that's just giving you the definition there. Here is the actual definition of a log function of base a, definition of an exponential function base a. So we're given the definitions, which come from pre-cal, and then we'll actually look at the derivatives of those. So if you've got a function with a base a being anything, okay, you would take the derivative of a to the x. It would be ln of a, thinking about actually just kind of the definition there. It would be ln of a times a to the x. Now these, you are not expected, of course, to memorize these. You're not expected to. They're a little bit tougher to memorize. So that's the derivative of a to the x. It would be ln of a, which is just a natural log of a number, times a to the x power. Okay? Remember how e to the x is its own derivative? This is kind of similar. Remember the function e to the x we talked about, I think, in the previous section? Well, it's its own derivative. Well, it's kind of similar when you have a base other than e as well. You still have its own derivative, but it is still times a constant here. ln of a is just going to be some number, some constant. Okay, it's just not a perfect whole number, but it is a number. Then you've got, let's suppose you've got a function within a. So the derivative of a to the u would still be ln of a times a to the u, but then times the derivative of u with respect to x. Okay, so a little bit more to do here when you got a composite within it. Take the derivative of the u function, the inside function. Okay. Let's say we look at maybe one or two of those before we end this video. Alright, so thinking about what we know as far as, let me make sure I mention this. The derivative of log base a of x, that is 1 over ln of a. Remember, ln of a is still just a constant, x. 1 over ln of a, x. Okay, and that is because, again, this is a constant. Derivative of log x would just, if this was a base 10 or base e, it would just be 1 over x. But then we've got that constant there, ln of a. Here, if you've got a composite function within it, it's still 1 over ln of a times u this time, of course, keeping the u, and then times the derivative of u itself. So let me look at that so you can see what I mean. Here you've got derivative of 2 to the 3x, so you got a base of 2 this time. Okay, so think about it. Derivative base of 2, okay, it's going to be ln of 2, okay, and then keeping the 2 to the x, so it'll be 2 to the 3x, and then we'll take the derivative of the inside of x. So it's more so this one actually. Ln of, I'm actually going to write that. I'm going to write that over here on this side. Ln of a to the u, and then du with respect to dx. And that was the derivative of u. Okay? So I'm going to apply that. So right here, I've got ln of 2, this is ln of a, so ln of 2, the a is 2, times 2 to the 3x, and then that would be times the derivative of u, times the inside derivative, times the derivative of the inside function, which is u3. And I could honestly just leave it because ln of 2 won't multiply any simpler to that 3, and then I got 2 to the 3x. All I did was bring 3 up front. But that's all. That's really all I can do. This is a log base 10, so where I have log base a of some function, and I'm going to call it function u. And I'm looking for the derivative of it, and that would be, according to the rule, log base a of u, that would be 1 over ln of a times u, and then times the derivative of the inside derivative of u. Okay, so that would be 1 over, and again, we will not ever have to memorize these, ln of a times u, and then times the derivative of u with respect to x. Okay, so our a is 10 in this case, so that would be 1 over ln of 10, okay, so our base is 10, all right, and then times just the cosine of x. The u stays the same. The u right here is cosine of x. This is our u. Okay, and then I say times the derivative of u itself. The derivative of cosine x is a negative sine x. Okay, so the u function, because this is basically what I'm saying is this is log base 10 of u, where u is cosine x. So I took the derivative with respect to u, so I have 1 over ln of 10 u, and then times the derivative of u itself. So derivative of u, negative sine x. And all I'm going to do is put that on top and bring that negative out front. Ln of 10 times cosine x. You could clean it up even further if you wanted to. Technically, sine over cosine is tangent, so we could say negative 1 over ln of 10 tan x, if we wanted to. We very well could. Okay? Sometimes you may have to rewrite an expression before you're able to actually simplify it. Like this log problem here, we might need to break it apart, expand it out using the rule for log expansion. So this is log base 3 of x squared, or square root of x. And I'm going to say minus log base 3 of x plus 5. Now, why was I able to do that? Because this is the log of this entire function, log base 3 of this whole function here. This is a quotient. so we can apply the quotient rule for logs. I know it's a lot of rules, and they're similar names. They just are different depending upon what you're working with. So this is for expanding logarithmic functions. So what was a quotient? Because they have the same base, we can break them apart and write them as a difference of two logs with the same base. And then we can apply or take the derivative of each individual term. So this would be the log base 3 of x to the 1/2 power minus log base 3 of x plus 5. Okay? So we would have to rewrite that first before we would be able to simplify it. Then, of course, I would follow a similar pattern as to what I had up here when I take the derivative. So I have a log base 3, so let's say y prime. This would be 1 over, I'm talking about this first term, this would be 1 over. I had log base 3, that was log base a. So I have ln 3, keeping this part the same, x to the 1/2 power. Then I say times the derivative of the inside. The inside is the 1/2 power, the x to the 1/2 power. So I bring down that exponent and I lower it by 1. So I would get a negative 1/2 there. And I know that looks yucky. Okay? So you took the outer derivative first, which was the log derivative. Then you had to take the derivative of the inside function, which is that. Okay? Then you would do the same thing here. Minus 1 over ln of 3, keeping the x plus 5 the same, then times the derivative of the x plus 5, which would just be 1x. Well, technically just 1, I'm sorry, because the derivative of x is just 1. And then I could simplify this some more, clean it up some more. Let me show you what we would do here. That 1/2 I'm going to bring to the front. And then I still have the 1 over ln of 3, x to the 1/2. Then I have times 1 over x to the 1/2 there. So that was negative. So I brought it to the bottom. So this actually can clean up even nicer to just be 1 whole fraction, ln of 3. Oh, let me put that 2 down there, because I do have that 2. I'm going to put 2 ln of 3. I have x to the 1/2 times x to the 1/2, so I just got x. Because I'm basically going to keep the x and add the exponents. A half plus a half is just 1. Then I've got minus 1 over ln of 3, x plus 5. And there's nothing else I can do there. Maybe make it look weird. So 2 ln of 3, x, and I can't put the x in front with the 2, minus 1 over ln of 3 plus 5. Okay. I think that's about it with this section. Basically just practice. You need to practice. These problems are a little bit more involved, especially when you get into the log part. You may have to apply some algebraic expansion rules like I had to there. So just keep that in mind. But just practice. Practice makes perfect. I will make another video for 3.5 as well.